calculus. So this is the biggest problem. He able to segregate a small portion out of it, which is called d by dx or d by dt. So according to the property, according to the variable, what you want to vary, you can implement using differential calculus. Okay, the bigger problem now segregated into smaller problem. So this is first order derivative. So this is first order derivative. Okay, now you got smaller size of problem. So if smaller size is again difficult for you, what you'll do, you'll go for second order derivative. Okay, so until your problem is manageable level, you need to derive. So we derive two times. We derive two times. So if it is manageable level, you'll do all calculation, you'll get accurate results. You get accurate results, and you know where you took from. You apply the reverse operation called integration. Okay, if you do two derivation, then you need to do two integral. So how many times you are deriving, that many times you need to do reverse process. So this person single-handedly created differential calculus, integral calculus, applied for a scientific method, able to know that factor, gravitational factor, able to describe acceleration, inertia, velocity, momentum leads to action and reaction. So whatever the law applies for a small apple equally applies for a larger planetary object. So this is how classical physics works. This is how classical physics works. So each and everything becomes predictable. Each and everything becomes predictable. So if we compare classical and quantum, okay, if we compare classical and quantum, so consider this is atom, this is atom, this is the boundary line, this is the boundary line. So beyond atom, so classical physics works, classical physics works. But inside atom, quantum physics works, quantum physics works. What are the laws applies for classical physics will not work inside subatomic level. Okay, so this is contradictory. That is why whatever you learned in classical physics will not help to understand quantum world. So entirely different, entirely different. To understand this, we need to understand wave particle and duality. Okay, so the same thing will behave like a wave, will behave like a particle, which leads to duality. So for this, to demonstrate particle nature, we are taking a full bucket of sand and we are pouring it down. So this contains some slate. So slate contains two holes. Beneath this, we have one more slate. Okay, we have one more slate and it will form two distant piles. So if you are looking at your material, which is sand, so sand is made up of granular particles. So each and every particle is independent, freely flow. So because of gravitational pull, we have two slits. It is falling down. It is falling down. Okay. So each and every time, if the sand keep on pouring, it will slant away. It will slant away. So if you know your material, if you know your experimental setup, if you know how physics law works, you can reason out why it is happening or how it is happening. Okay. We do the same experiment. Now we are replacing the material with the water and we are keeping the same setup. We are keeping the same setup, slit 1, slit 2. Okay. So what we are doing in the left side, we are tapping. We are tapping, it will generate continuous ripples, water waves. So this water wave will pass through S1 and S2 in this same pattern. In this same pattern. Okay. So if you do the same experiment but different material, you'll get different phenomena. Different phenomena, but you are able to understand why it is happening. Why it is happening. Okay. So, but if you do the same experiment in quantum world, you'll get very, very unexpected results. So this is very strange. Okay. So all this experiment, if you have prior knowledge, if you have how it is working, okay, you can predict, you can reason out. But if you do the same experiment in subatomic world, in quantum world, you'll get very, very unexpected results. So this is the major crux between classical physics and quantum physics. So we'll have some example. I'll skip this slide. I will share this slide. In free time, you can go. So because we have limited amount of time, we need to focus on important stuff. So now what we are doing the same experiment with the help of light bulb. So the setup is same, double slit experiment. So left side we are keeping a light and right side we are keeping a blackboard. And what we are doing, switch on to that light and it will generate 360-degree light waves. 360-degree light waves. So this light wave will go through two slits. So because of the difference, at some point it will collide, it will create darker band. At some point it will go along, it will create lighter band, amplify. Okay, because of phase difference and phase similarity, we will get continuous output. I'll zoom it for your convenience. So in this experiment, we generated light wave and we are splitting into two slits because of interference. Some point you will get lighter band, some point you will get darker band because of interference pattern. So this is one phenomena where light behaves like water. If you do the same experiment with little modification, so this is called detector. So these are called detector. We are adding one detector and one more detector over here. And what this detector will do, it will act like door. So you need to close one of the door and you need to open one of the door at one point of time. If you do so, you get output for this. Okay, then you reverse this process. Okay, if you close this door, if you open this door, if you close this, if you open, then you get this output. So at one point of time, you are opening only one of the door and closing another door. So there is no interference happening. If there is no interference, you will get particle-like output. This is equivalent to water. This is equivalent to sand. So from this experiment, you can conclude if you are not observing your light, it will behave like a wave. It will spread like a wave. Okay. If you try to control your light, if you try to observe your light, it will collapse. It will collapse and it will appear like a particle. So the entire wave will get collapsed and you will see one point of location, in this entire wave. So this depicts duality of light. Now what we are doing little modification about this experiment. Now we have electron gun. So here we are generating electron one by one, like a particle. So here the origin is particle. Okay. So this particle will go through upslit sometimes. Okay. It will reach over here. So it will go down slit sometimes. It will reach over here. So we got only two bands, right? So band 1 and band 2. So this is what we observed in previous slide. So if you are generating particle, you will get only two bands. But look at the output. Got so much of bands, continuous bands. It is the output for waves. So even though our origin is particle, the observed output is like wave. Can anybody explain why it is happening or how it is happening? Are you able to guess? Put in the chat box. Are you able to observe? Are you able to recognize? We are generating particle, but why we observed a wave output? Okay. What about that hypothesis? Can you elaborate?
Sir, we are scared of quantum computing. We feel it's very difficult.
No, ma'am, no, because we need to refresh from school. If I'm teaching this content to school students, they will answer immediately. So the more we are getting age, above 30, above 35, above 40, more difficult to learn quantum. Definitely, definitely you can speak. The more degree you have, more
Sir.
difficulty to learn. Yes, sir. Yes, sir.
Uh, so, sir, what I understand is that there was a PhD student named D. Broglie, and
Yes,
he
sir.
suggested a hypothesis that every particle that it has dual nature. That is sometimes it behaves as light and some behaves as wave, and sometimes it will behave as a particle.
Exactly, sir.
And he thought it was random, but that is not random. There is something
Exact.
called de Broglie wavelength, that is the ratio of Planck's constant and the momentum.
Very good, sir. Very good, sir. So particle one will go to slit one and it will reach over here. Okay. At the same time, the same particle can divide into two halves. It will go through both slit and it will reach over here. So same particle can behave like wave. Okay. So after the slit, it will combine together and behave like a particle. So we cannot predict how it going to behave at what point of time, at what point of location. That is why we got wave-like output. So it also contains the knowledge about particle also. Right? So this is so much confusing because if you try to understand with your classical physics, you cannot understand the output of quantum experiment. So this line is very, very important. This line is very, very important. So if you are doing any quantum experiment, the outcome is nearly impossible to understand nor to explain because it behaves in very, very random fashion. So each and every time the outcomes varies. This is very important thing you need to note down. If you are doing any quantum experiment, there is no static output. Each and every time the output varies. So I will give you some example. I will give you some example. Take 2 plus 2. Take 2 plus 2. If you're using your laptop or classical computer, and if you're using quantum computer, if you're using quantum computer. So in classical, you know your input A equal to 2, B equal to 2, and C equal to A plus B. So plus is operation. If you write program for this, if you're executing for first time, the output is 4. If you're executing for second time, the output is 4. If you're executing third time, the output is 4. If you're executing for fourth time, the output is 4. So each and every time, if you know your input, if you know your process, so then it becomes deterministic. Deterministic. But in case of quantum, the input is same, everything is same, everything is same. If you are writing program in quantum computer, first time you'll get output as 4. Second time you'll get output as 3. Third time you'll get output as 2. And fourth time you'll get output as 1. So this is probabilistic computing. This is probabilistic computing. So each and every time output varies due to random nature. Due to random nature. This is due to random. So you cannot fix in quantum. Each and every time your output varies. So if you're running for 4 times, you'll get maximum confusion about your output. Okay. To understand this, we need to run multiple times. Take an example of 1,000 times. If you're running for 1,000 times, then you will have probability distribution. 80% of the time, you'll get answer as 4. 10% of the time, you'll get answer as 3. And 7% of time, you'll get answer as 2. And 3% of the time, you'll get answer as 1. So here, all the answers are correct. Here, all the answers are correct because it is deterministic in nature. But here, only the first time the answer is correct. Remaining 3 times the answer is wrong. But if you are running for multiple times, more number of time you'll get correct answer. More number of time you will get correct answer. And less number of time you get wrong answer. The much you are running in your quantum system, the much correct answer you will get. The higher the frequency. So this is due to probabilistic nature. This is due to probabilistic nature. Okay. So I'll describe qubit. I'll describe qubit. So this is the depiction about qubit. This is the depiction about qubit. So we'll start from basics. Bit is a binary digit. It contains only one of the two states at a point of time. Imagine if you have a flip-flop, if you have a transistor, if you have a register. At one particular point of time, you're able to show only one data, able to represent only one data, one state. Okay. Imagine if you have a capacitor. If you have a capacitor, so if you want to show 0, what you need to do? You need to discharge. You need to fully discharge. You need to fully discharge. Suppose if you want to show data 1, capacitor equal to data 1, then what you need to do? We need one instruction cycle. One instruction cycle, which is the time required to transit from 0 to 1. Imagine one instruction cycle is 1 second. 1 second. Then what do? You physically fully charge that capacitor to depict state 1. Okay. So for a single device, you need one instruction cycle between two data. Okay. In case of quantum bit, we have an electron. We have an electron. This electron can move from state 0 to state 1 randomly, in random fashion. Okay. But what is the beauty? It is in superposition. At the same time, it is pointing to 0, as also it is pointing to state 1. This combination it cannot have. This is differentiable. This is totally different. But in quantum, you have combination of zeros and 1 at the same time. So within one instruction cycle, we are able to point both value 0 as plus 1. So this is the capacity of quantum. If you understand this, you can understand if you have 2 qubits, you can point 4 different combinations 0, 0, 0, 1, 1, 0, 1, 1 due to superposition. Due to superposition. So this is superposition state. This is superposition state. It is in between 0 and 1. Okay. In case of classical, if you have two devices, two capacitor, okay, if you want to show 0, 0, then you need to fully discharge. Suppose if you want to represent 0, 1, we need one instruction cycle. Then if you want to represent 1, 0, then you need one more instruction cycle. Then you need to represent 1, 1, you need to have one more instruction cycle. So classical, you need 4 instruction cycle. In classical, you need 4 instruction cycle. But in quantum, within single instruction cycle, you can represent all combination together. All combination together. So that is how you can represent more number of information in less number of time. So in quantum, every operation is parallel, massively parallel. So this is sequential, right? So whatever the supercomputer you're using, it is sequential. After some point of time, it depends upon sequential operation. Imagine if you have 3 qubits, 3 quantum bits, 3 electrons or 3 photons. It means you can represent 8 combinations simultaneously. Not only representing, you can do computation also. So this is the beauty about quantum, right? So we can understand what is the impact of adding 1 qubit. So 1 qubit will have 2 different states at the same time. If you're adding one more qubit, which will double the number of possible states. And this increase is exponential. So 1 qubit, 2 states. So look at this slide. If I am adding one more qubit, becomes double, becomes 4 states. If I add one more qubit, becomes 8. Are you able to recognize how much increase is happening? So keep on add one qubit. You will get 50 qubit. You will get 1 followed by 11 zero states. 11 zero states. Huge amount of data. Okay. Can anybody relate this point to any one of our previous slides? Adding one more qubit will double the number of possible states. Please put in the chat box. Yes, please put in the chat box. So where we cover this topic. Adding one qubit will double the number of possible states. Superposition, okay. Previous slide. For clue, that is the first topic we covered. First slide. We discussed about one law, right? Initially, we discussed about one law. What is that law? We discussed about Moore's law. Exactly, Professor. We discussed about Moore's law. So we are able to achieve Moore's law with the help of this adding one more qubit. Adding one more qubit. So what we'll do, we'll discuss how qubit represents. How qubit represents. So this is the visualization of a qubit. Okay. So imagine your electron located here. So this will move to state 0. This will move to state 1 randomly. So it won't stop. So it will keep on moving. Okay. So this vector is called quantum state vector. Quantum state vector. So generated from origin. Okay. The radius is equal to 1. It means it is a unit circle. It is a unit circle. So this is a visualization tool to view your block sphere, to view a quantum bit. Okay. So quantum bit contains two states, basis state, like x-axis, y-axis in graph. It contains state 0 and state 1. So psi is called superposition state. Now it is in superposition. It is in between state 0 and state 1. Okay. So what I do, I try to depict this qubit. I try to depict this qubit using this tool. So all of you go to this composer. So composer is here. I'll share this link to you. So all of you go to this link I shared over here. So without login also you're able to use this tool. Without login also you're able to use this tool. I'll check my time. So 7:30 I have one more session with another ATAL FDP. Today hectic. I hope all of you are able to reach that tool. So this is how it looks like. This is how it looks like. So you can see Q0, Q1, Q2, Q3, it means 4 quantum bits, and C4, it contains 4 classical bits. So whatever you do operation in quantum, finally you need to store in your classical register. So during that time, superposition state will get collapse. Superposition state will get collapse. So even though it is in between 0 and 1, but when you do measurement, either it will go to 0 or either it will go to 1 by force. Okay. So for simplicity, I am deleting 3 qubits and keeping only 1 qubit for understanding purpose. So we have Q0. Similarly, you do for C4, C3, C2. So keep only 1 qubit. So keep only 1 qubit. So you can resize your window in such a way. So you can do also. can resize your window in this way. Okay, so for one qubit, we have combination of state 0 and state 1. So state 0 exists in North Pole. So state 0 exists in North Pole. Okay, state 1 exists in South Pole. So this is equivalent to binary 0. This is equivalent to binary 1. Imagine in this way. For understanding purpose, so this is binary 0, binary 1. Now what we are doing, all qubits in IBM Qiskit started from stage 0. IBM Qiskit started from stage 0. Stage 0. So stage 0 means off state. So where we are representing stage 0 in North Pole. That is why it is pointing to North Pole. Okay. To understand this, what we are doing, we are implementing NOT gate. So the second gate is called NOT gate. Look at your window. The second gate is NOT gate, looking like crossfire. Looking like crossfire. So by logic, if we start from stage 0 off state, okay, we implemented NOT gate. What is the logic of NOT gate? It will create negotiation. From stage 0, it will move to state 1. So state 1 means on state. On state means power supply will happen in this wire. Power supply will happen in this wire. So that is why it is moving through stage 0 to state 1. So this is stage 0, this is state 1. This is happened due to this NOT gate. So look at this. Look at this. So you can see changes over here. Gray color now turn into blue color. Okay, North Pole now pointing to South Pole. So previously it is pointing to 0, now come to 1, 0 to 1. Okay, so this is simplest demonstration I showed over here. If you want to know its equivalent coding, you can click here. You can click Qiskit. So you can see equivalent Python code. So Qiskit stands for, so I will write abbreviation. Qiskit stands for Quantum Information Science Toolkit. Quantum Information Science Toolkit. So this is the abbreviation. Okay. So this tool will give the whole idea about how to use your quantum gates to construct quantum circuit. So you can do in multiple ways. Either you can do by a graphical mode or coding mode. Okay. So NOT gate is very familiar for us, each one of us. Okay. So what you do, click this NOT gate, press delete button. Now click H gate and place over here. So this H gate will create equal superposition. So what this gate will do, this H gate will create equal superposition. Equal superposition. So that is why it is pointing to North Pole and South Pole simultaneously. So in classical, you don't have any comparison to Hadamard gate. Okay. So to get information from this, information from this, you need to do drag and drop this measurement gate. So all of you drag and drop this measurement gate. So once you do, superposition state will get collapse. Superposition state will get collapse. You'll get only one possible outcome, either 0 or 1. So this is how we are able to create quantum circuit and be able to get information in classical data form. So I try to stop over here. If you have any doubt, you can ask me. So if you go to all these courses, you can learn how to create quantum simulation. So go to view all courses. So start from basic quantum information, go for quantum algorithm, then you're able to write quantum simulation. Okay, quantum computing practice will help you to write program until more than 100 qubits. Then you can go for quantum chemistry, you can do chemical reaction, you can do simulation using this tool. I explain all this stuff for you. So if you have any doubt, you can ask me. I'm open to questions. I will share my social media profile. You can follow me. You can give connection request. Either way, you can do. So whatever happen within India or outside India, especially in quantum domain, I will keep on post over there.
Participants can unmute themselves and ask the questions.
Yes, I will explain Hadamard gate. I'll explain because time is very, very limited. That is why I'm thinking. I tried to explain superposition if time permits. Okay, take an example of tossing a coin. Take an example of tossing a coin. Okay. So superposition is one phenomena in quantum, one position over another position at the same time. Take an example of tossing a coin. So coin contains two faces, head or tail. Okay, when you toss, superposition is created. Superposition is created. Okay. If you are looking at your coin during the air flip, you can see both head and tail simultaneously. Okay, so during the air flip, so 50% of the chance you will get head and 50% of the chance it is being in tail position. Then you can say with 100%, allow the coin to freely fall. After some point of time, it will settle down. It will settle down. During that time, you do measurement. You do measurement and observation. Observation. So during the superposition, it is in and logic. So both head and tail. But after measurement, you can see 100% of the time it is facing to head or 100% of the time it is facing to tail. So this is OR logic. This is OR logic. Okay. This creating superposition, tossing the coin. Okay. This superposition is called Hadamard gate. This superposition is called Hadamard gate. What you are doing over here, what you are doing over here, what you are doing over here, we are creating superposition. So I'll go to composer. I'll go to composer. I'll go to composer. So initially it will give 4 qubits. Now what you're supposed to do, you need to create only 1 qubit. So delete remaining one. So click Q0 minus or bin button. Okay, we have only 1 qubit. Now it is in stage 0. But if we create Hadamard gate, it will create equal superposition like tossing a coin. If you toss a coin, what happens? The superposition created 50% it will show head, 50% it will show tail. So this is the logic I can show for you. Now you tossed your coin. Now you tossed your qubit. If you do measurement, what happens? It will show only one possible outcome. Now I got state 0. Sometimes I will get state 1. So randomly I will get value if you do measurement over your superposition qubit. Is it clear now? Thank you all.
Hello, sir.
Yes, ma'am.
Sir, one question I would like to ask.
Yes, ma'am.
How would machine learning or AI contribute to faster quantum simulations?
It is vice versa. So much of problem happening in quantum, like error correction, because noise is very important topic in quantum. Whatever happens outside, it will impact quantum system. So if there is no noise from outside, internally also quantum system has some noise. So each and every time this noise will accumulate. So using AI and machine learning algorithm, we try to reduce that noise. So all of us know we studied about error correction theory. So information theory, information coding theory. So same way we have quantum information theory. So in that subject, they majorly focusing on quantum error correction. So quantum will support to improve AAML. Also AAML also help to improve quantum. So vice versa.
Okay, sir.
You,
Thank you.
we cannot do chemical reaction in supercomputer, but we can do chemical reaction using a quantum computer. So supercomputer will fail if it want to create a chemical reaction, if it want to simulate chemical reaction. And quantum computer can break any cyber security protocol. So RSA algorithm can be easily breakable by Shor's algorithm. If you go and Dell Shor's algorithm, it will break easily. But that quantum computer, the capacity is not built. If someday quantum computer built within 15 years or 20 years, it will break all our passwords within a fraction of minutes.
Okay, thank you, sir.
Thank you, ma'am. Thank you.
Any other questions from the participants?
So if you don't have question right now, you can contact me, you can communicate me at any point of time. Thank you all. Thank you, ma'am.
Okay, okay. Okay, sir. I would like to just end with the vote of thanks. On behalf of the organizing team and all the participants, I extend our sincere and heartfelt thanks to Dr. Jaykumar for delivering such an insightful and engaging session on quantum computing simulation acceleration. Sir, your clear explanation, real world perspectives, and deep technical insights have greatly enhanced our understanding of this advanced and emerging area of quantum computing. The way you connected theoretical concepts with practical applications and future directions were truly inspiring and valuable for all of us. We are grateful for your time, dedication, and willingness to share your vast knowledge and experience with us. This session has not only enriched our learning, but also motivated us to explore further research and innovation in quantum technologies. Once again, thank you, sir, for your excellent contribution and for making this session a great success. We look
Thank you.
forward to more we look forward to more such enlightening interactions with you in the future. Thank you very much, sir.
Sure, sure.
I request all the participants to kindly turn on their cameras so that we can take a group photograph.
Hello, is it audible?
Yeah, thank you, everyone.
Yeah. So,
Dr. Ajay?
yeah.
Yes, sir,
Hello.
audible, sir. And thank you for joining.
Okay. So thank you. And should I start?
Just a sec, sir, we are giving just 2 minutes break and then we'll start.
Okay. Okay.
Hello, Dr. Ashish.
Yes, ma'am.
Please start the session.
Yeah, just a second, ma'am. Good evening, everyone, and welcome to the session 4 of this faculty development program. For this session, we have Dr. Ajay Singh with us, and it's my privilege to introduce the audience. Dr. Ajay, Professor Physics Department, Indian Institute of Technology, Roorkee, have more than 30 years post-PhD research and teaching experience. Among the leading researchers in the area of theoretical quantum condensed matter physics, with academic administration at different levels. His current research interests lie in theoretical modeling and computational simulations of electronic properties in strongly correlated low dimensia L nanospace quantum materials such as superconductor, quantum dots, hybrid Josephson junction, finite and infinite correlation regimes. Superconducting qubits-based quantum computations such as the potential superconducting circuit for quantum information processing, electronic band structuring twisted multilayer graphene nanostructures, and theoretical aspects of high temperature, possible room temperature superconductivity in ion and couplets within many body strongly correlated quantum theoretical formalisms, finite and infinite correlation regimes. After completing his PhD on superconductivity in nanoband system in 1995, under supervision of Professor R.S. Tripathi, Dr. Ajay joined as a condensed matter theory group, working as a strongly correlated system under Professor S.K. Joshi, former DG CSIR, at National Physics Laboratory in New Delhi. He joined in 1996 as a project scientist and worked on transparent behavior of strongly correlated electronic systems, a DST-sponsored project research. Dr. Ajay joined IIT Roorkee in 2008. Before 2008, he had many other engagements. He served as an assistant professor in Department of Physics at GB Pant University, Pantnagar. Dr. Ajay also has undertaken many prominent international visits, the IESC Congress, Paris, France, the Abdus Salam International Center for Theoretical Physics in Italy, International Institute of Advanced Scientific Studies, University of Salinum in Italy, Cavendish Laboratory, London, University of Cambridge, UK, and many more. He has worked, he has published more than 133 journal papers in peer-reviewed international journals. He has guided 11 PhD students and 30 master students, and he has been working as a research guide for many projects. He has conducted many international, he has presented talks and presentations in many international conferences and national seminars. Dr. Ajay was awarded by a Young Scientist Award by Government of Uttarakhand, India, for cutting-edge research contribution in the field of high-temperature superconductivity. Dr. Ajay has also been awarded Inspire Mentorship by Department of Science and Technology, Government of India, for his continuous outstanding academic BTech, MSc, and PhD level teaching and leading research contributions to inspire young minds. Dr. Ajay granted membership of IAS, expert member of UPSC New Delhi, RPSC, JEE Advanced, and UK Higher Education Selection and HPPSC. Also member of several educational boards and on the role of a reviewer panel of reputed peer-reviewed national and international journals like Springer, IOP, Elsewhere, Springer Verlog, etc. So we are very pleased to have such an eminent personality as a speaker for this session. And on behalf of the entire organizing team, I welcome Dr. Ajay and request him to start the session. Thank you very much, sir. Over to you, sir.
Okay, so should I share my slide? Okay, thank you to Neha and the organizer to introduce. Is it audible to everybody?
Yes, sir. Yes, sir.
Slides. Yes, it's shared.
Yes, sir. It is visible. Just make it full screen, please.
Okay. Just a minute. So I think it is now
Yes, sir.
quite
Perfect.
visible.
Perfect.
Yeah. So thank you for your very, can say, deep introduction. So I'm very grateful to the organizer to give me this privilege. And my topic is how the paradigm of quantum science and how superconducting qubit is being used for information processing and quantum computing. So this is actually a faculty development program at VCET, and I'm again very thankful to the organizers to interact with the young learning faculty, and what I have learned and I want to basically convey to you is available in this slide. So if we basically introduce with the world of quantum computing and how it is related to the the qubit and bits. There are two groups. One is how quantum computing fundamentals are connected to the qubit, and what are the practical algorithm on the other side. Okay, so I'll basically design this whole talk in these two groups. First, I'll introduce you what is the bit and qubit and what are the important qubit properties that is basically used to build quantum computers. And there are several ways to develop quantum computers currently. So, but my expertise is in the superconducting qubit-based quantum computing and its operation. So, starting point of any quantum or any computing is gates. So, we use logic gates and set up these logic gates to the you can say a source of transferring information through some material. The material must have certain properties. So you can have multiple qubit gates. Now our country is trying to follow 3 qubit gates, and we are basically leading towards getting a mature, I can say, research infrastructure in terms of quantum computing, as a lot of funds are available. And the deep intricacies involved in the quantum circuit, multiple qubits. The other side is there are what are the algorithm and practical logistic which can be used to basically scale and optimize the system. So that will be the later part. So since you are learning and there are initial talks, so the first question is why quantum computers? So what will happen if we basically develop quantum computers, and why not the semiconducting quantum system, which is basically the computer which I'm using just like this, based on the semiconducting device where you have a band gap is being used. So the point is currently we have a lot of data, and these data are random. They are increasing exponentially, and quantum computer will basically give us a process which is working at a very high speed, maybe several times higher than the semiconducting device. And there are also some mandatory requirement which can be attained technologically through some, you can say, research design. First thing is the material we have nowadays is giving you qubits at very low temperature. So we need to design first low temperature. We need to basically suppress the vibration, or a system should be isolated from rest of the world in order to have coherent information. And there should be no interference among the states, or it should be basically blocked. And the magnetic states or magnetism basically should not be there, or we should make it isolate, or if it is the part of the system, we should make a localized magnetism and connect it to some coherence time. Okay, so there are quantum algorithms which are based on these requirements, and these quantum algorithms basically provide us the final result in the form of basically qubit, which is said to be to the proper, you can say, material-based requirement. Well, in the next few slides, you will know. And to construct, basic aim is to construct a gate based on the qubit. And to construct a gate, you require basically a material. So before going ahead, let me recap you. I think in some of the introductory talk, you may have learned what are the intricacies of quantum mechanics and diversion from the old quantum hypothesis that give you a new idea, which is coined by Feynman. So this actually history started right from 1935. In 1905, the quantum results were basically discovered, most of the quantum physics by Einstein. And there was a famous paradox, EPR paradox, which says the Schrodinger equation is in danger. It is not solvable because it requires partial boundary conditions. So in the usual mathematical paradigm, the Schrodinger equation does not solve exactly. So to solve Schrodinger equation, the reason is the eigenstates are basically entangled. You cannot separate out the quantum states. They are having certain kind of entanglement, and this entanglement basically make the Schrodinger equation partial. So it is tough to solve. And on the edge of this entanglement, in 1964, around 35 years later, there is a Bell inequality which says that there is no analogy from classical to quantum. If you look at classical mechanics, is very sophisticated. You start with the Lagrangian from Hamiltonian approach, and there is a lot of very deep symmetry and mathematics involved. And at that time, I think even today, we cannot have a very smooth crossover from quantum to from classical to quantum. But these things should not stop you to understand more advanced level quantum mechanics, because those things can be understood from the current technological aspect. They can help you to understand back and forth. And then based on our informations of quantum entanglement, it was basically developed by Shannon that one can have quantum information theory, and this quantum information theory can be generalized to basically a coupled state, and you can transfer information from one point to a very large distance. And the Richard Feynman, who was on the backbone of the quantum computing at the Caltech, a theorist who designed the quantum computing and atom bomb chair for US. He was the person who has given the fundamental basis for a universal quantum computer. And to design the material, you require quantum cryptography to fit the material into a proper design. Okay, so in the late 19th or early 20th century, there is a huge quantum computing leap, and there were the very famous Da Vinci criterion. What are the properties should be of a quantum state that should be basically verify that whether these quantum system can be used to have quantum computing or not, and there should be some error correction also. So if I go step by step, the IBM has been first to implement the quantum computing in 2001. And if you look at now, 2025, we are now having a huge quantum mission and funds, but there's few countries already taken lead. We should do much harder work. Okay. So in 2010, the EU already have the visibility of a commercial quantum system with 128 qubit and discrete optimization. And then in 2014, you have quantum teleportation, and you have the calculation of the hidden molecule energy on the base of quantum computing. So in 16, the implementation of quantum circuit has given us the IBM cloud, and now there is a 53 qubit system. The Eagle, another group of IBM, has generated 127 bits, and we are talking about now 151. And now we have generated infrastructure. Government has make a national quantum mission to make different spike and group who are working in this direction. So there's a huge opportunity. So with this, you can say background, let me start you what is the real bit and qubit system. So a bit, you know, to transfer the informations, you have to digitalize it in terms of 0 or 1, because either state is high or low. It can be done by a semiconducting system like your laptop, mobile. They are all based on semiconductors because there is a band gap. So you can make a switch using this band gap by on or off state, and using 0 and 1 state, you can digitalize it. You can get certain logics, and using these logic, you can make basically a sort of string of uh, uh, you can say conversion of your data into a digital string. So this story is already known. The lot of design of computers, laptop, the device which is in your hand with very high speed now available. And the next is your quantum bit. So in quantum bit, instead of 0 and 1, you can also have a combination of 0 and 1, and this can be done through block states. And the smallest unit of computer cannot be now 0 and 1. It can be 0, 1, and also their superposition. So 0, 1 state can have very large superpositions. So this superposition will help you to speed up the system, because your state are not blocked to 0 and 1. It can be between 0 and 1 anywhere depending on the circuit block state. Okay, so the applications of these quantum computers is huge. Nowadays, you can develop the machine learning and algorithms, AI, the machine design, drug discovery. You can use the cybersecurity, cryptography, and financial modeling. So right from drugs to the cybersecurity, which is very important, and you can design new material, and you can use cryptography to interface the different material, and also you can predict the what is happening to the stock market using these models. So nowadays we call as embedded AI. You use science, then you use a AI based model, use both, then get another data, use those data, find another modeling, and you can have embedded structures, which may give you some new results and new ideas and new applications. So a qubit must have these following 5 properties, and these properties were settled by Da Vinci criterion. So qubit technology must have possible superposition, means the state must be entangled, and this is done by superposition. The state should have a tunneling and a possible annealing. The meaning is you have amplitude, then you have a potential. This potential barrier you have to cross at the cost of some diminishing amplitude, but there is finite probability on the right hand side. And the quantum system, based on these ideas, there are many quantum systems. You on top of the quantum hardware system is superconducting qubit, then NMR, then you have Marana, fermion, and photonic, and also the trapped ion or quantum dot, which are nanostructures. So nowadays you are using quantum dot with superconducting structure, which is one of the promising candidate, and also NMR. And using this, the different group is focusing on different aspect. This color can give you an idea how the different material can be used by the different group to specialize. And this is actually just like a double well tunneling. So the whole idea of the entanglement is basically a tunneling. a local minimum to global minimum. And this can be done through some junctions. Okay. So a qubit property, which is based on different materials, basically now you are having just like polarized photons, then you have multiple discrete energy levels, you have superconducting transmon qubit, which is the work which our group is working, and nuclear spin also. But out of these all structures, the superposition is very well established in superconducting transmon qubit. And idea is that you can have a block sphere. Block sphere means you have localized states. They are not K dependent. They are only on theta and phi dependent. Okay, zenith and azimuth angle. And these theta and phi variation can give you so many states between 1 and 0. So it is 0 and 1, 0 plus minus under root 2. So a combination of that. Okay, so you can have the algorithm. You can have then using hardware quantum gates, and using these quantum gates you can generate quantum circuits. So this is the superposition sphere, which is called block sphere, and you can basically eliminate these unwanted coupled state by using quantum circuit. This is called quantum driven interference, and lead to a solution which can give you a isolated quantum state, which is basically having a sense of uh, these all states. So this is your input and this is your output through this quantum circuit. So this is the broad way, and to implement it, there are various steps. You require various kind of expertise available. Okay. So if you have any question, you can stop me and indicate that you have certain queries. So for quantum gates, you already know that you can have X gate, Z gate, H gate, and they depend on the matrix element. And this matrix element, actually alpha and beta can never be one. They are different. That's why you have different combinations. So you can generate various gates by using the various matrix element. And there are also the two gates, which is C naught and swapping, which is basically having 4x4 matrix. Your whole aim is to find the diagonal element, because these diagonal elements are energy eigenvalues, which can give you the qubit. Okay. So a qubit quantum system is comprised of gates, and gate can use basically the a quantum circuit, and then on this quantum circuit you require to have the you can say understanding of input and output in terms of a language that's called algorithm. So this is the whole setup of a quantum computer which can be used. So for quantum gate you require a particular material. To have a particular material, you have to identify whether qubit and the fidelity conditions are verified. Then a circuit can be designed. Then quantum algorithm can be basically implemented. So this is the whole story, which everyone is talking in different tune. Okay. So qubit-based gates, then qubit-based computation and gates. Then there are quantum algorithm, which is DJ algorithm is the first one which demonstrate that the significance of quantum amplitude can be taken into account. It can be positive and negative. A quantum amplitude can be positive and negative both, but a classical probability is always non-negative. So unlike the classical computer, the quantum computer is more versatile and its domain will be much higher. And there are various algorithm which is being used by name of the various scientists. But out of these, the idea is that you are having, sorry, the superconducting qubit based on the D Vinci criterion. It is given by 2000, and it was first organized by a set of characteristics based on a hardware to develop a quantum computer. And these properties which are here, first is that your quantum computing material must be having a scalable system. and it should be able to have some initial state of a qubit, and there should be a long coherence time. It should not be idle, so that the coherence is destroyed by some external field. It should have a universal category. It should not change or hijack its property in the field or in the vicinity of other material. The qubit scientific measurement must have capability to basically convert into a stationary or a moving qubit, and it's also be able to transmit the qubit and its location back. And these all property are embedded in the well-known superconducting qubit. It fulfill all these 5 Da Vinci criterion. So nowadays it is important qubit-based idea. And the rest of the lectures, my focus will be on how superconducting qubit basically built to give you the modeling of quantum computing. So to understand qubit, let's start with the superconducting bound state. So most of you might have learned by now that you have materials where the state of the system can generate the current, which can be having zero resistance or resistance close to zero. So you have no vibrations. The vibrations actually quench down at low temperature, and basically the phonon are basically going to couple the electron with the positive spin. So there is an entity that's called Cooper pair, and they are bosons. These bosons have very high coherence length, and also they have a bound state, which is generated by quanta of vibrational energy. And this boson-like behavior basically generated by by Cooper, one of the scientists, Cooper, on that name, drummer creature was staples. So the basic idea, there was the 3 scientists Bardeen. It is a semiconducting engineer, electrical engineer, who has 2 Nobel Prize, then Cooper and Schiffer. They were the 2 theoreticians who has given the idea that BCS theory can explain normal means it is the standard BCS superconductor, and this is how Cooper pair can transmit through the atoms. And one of the interesting thing is that this is not a long range feature. The Cooper pair bound, and only nearby atoms are get attracted towards electron, not the next neighbor. They are intact. You can say the phonon which is being used are local, they are virtual, and the bound state is not basically in the whole region. It is in the outer periphery as a spherical segment where all k and minus k state are filled and bound, and this gap in this region give you the binding energy of Cooper pair. So the phonon mediated Cooper pair are there, and the coherence length is of the order of centimeter. So that means a superconductor can be used to interface with a quantum material and can have a very large coherence length to the tune of centimeter order, and the gap around the Fermi level is continuous. It's called the S-wave gap. So here it is the superconductor where you have the normal metal. It is just like V-shape, and the superconductor has a parabolic gap. So from at the Fermi level, there is a gap of order delta zero, which can be mapped with the transition temperature, and the temperature dependent of the gap can write by this equation. These are the famous non-BCS equations, and the transition temperature is basically depend on the Debye energy and also the exponentiation of inverse of the Coulomb energy and density of state at Fermi level. So larger the density of state at Fermi level, larger the transition temperature. But this is a metal. The metal increases its state as basically square root of energy. So when a metal try to become a superconductor, the states around the Fermi level are bound by the gap 2 delta 0, below the Fermi level delta 0, and above. And these states are basically coherent, and electrons are bound. and they can be used to develop qubits. Now, what happened? Such kind of a gap is a superconducting gap. But in semiconductor, you also see a gap, indirect gap here. And you also generate the N-type and P-type state by doping. So this thing can be done here to identify a superconducting qubit. Okay, so a Cooper pair can be used to transfer or couple through a quantum dot, generate Josephson junctions, means Cooper pair can tunnel just like electron from superconducting material to the other side. And this phenomena was given by Josephson. It was another Nobel Prize in this field. And this year Nobel Prize was also given a macroscopic Josephson effect. The phase difference of the, you can say, delta between the Cooper pair and other side of the Josephson effect can be changed, or it is basically sinusoidal. I equal to IC sine delta, and delta is actually the phase, which is the difference of the Cooper pair phase from left and right. So more the difference, more the sinic term, and the IC is called the critical current, which can be the maximum current can flow without generating magnetic field or destroying itself, because current also generates magnetic field. So magnetic field can basically destroy the coherence. So you have the phase, you have critical current, and these two parameters are important. And how they are important? Because this, if you look at the energy level of an oscillator are basically equispaced. This is ground state, and the excited state are equispaced. So if you replace the inductance by a Josephson effect, L by a Josephson, you can say tunneling. So you say there is a sinic term. So instead of having a parabolic, there is some width. So there is some broadening. And if you find the quantization of the state from ground to excited state, this is the largest, and this gap go on decreasing. So this can only be done by going from harmonic to enharmonic oscillator. So in the enharmonicity is due to the Josephson effect and the phase difference between the Cooper pair, which can be controlled. So these states, which is ground state and first excited state, these states are basically called block states. So quantum computing is a matter of not the ground state properties, just like your semiconducting device. It is the excited state property, which is controlled by changing the potential or by changing the phase in a device through using Josephson effect. And so you can have a macroscopic device which can generate the quantum properties, and the device is just like a harmonic oscillator, and you can have the blockage of the transition from 0 to 1 state, and also its combination. So you cannot allow the state to follow. So what happens if you look at the probability of a system to be in the ground state and in all the excited state is finite. So total probability is 1, but it is distributed. The probability in the ground state is maximum. The probability in the highest excited state is minimum, but there is finite. You are basically looking at it from ground state to excited state. The probability is only up to here, and the next second and third excited state are vacant. So you basically brought all the probability close to the ground state and the fifth excited state to make this flux to be, you can say, coherent and generate qubit. Okay. So this can be done by some nanostructure. It was basically predicted by Feynman that you can have quantum dots, which is just like artificial atom because they have discrete energy states, and these quantum dot can be used to develop the tunable hybrid quantum dot devices, which based on the Josephson tunneling, and they can be used for quantum hardware, superconducting quantum dot. So how the physics go? You have quantum dot, then the physics of quantum dot, you understand it's a 3D dot, 3D to 2D to 1D and to just a dot. So your density of state go like this. If it is metal, here you have steps, here you have spikes. Is one dimensional, but in a zero dimensional where all electrons are confined, the state are discrete. If they are discrete, your work is done. So you can combine these states with a superconductor. So what happens? The density of state can be changed from ground state to excited state. So this is the first excited state. This is the second. You can see the eigenstate of the ground state is orthogonal to the first excited state, which guarantee you that there is no overlap of the ground and excited state, because the wave function where maximum is the ground state is minimum in the first excited state. And this orthogonality give you that the states above the excited state are not coupled. Only the ground state and the first excited state are combinations. So this thing can be intelligently built by using nanostructures, which are zero-dimensional quantum dot. And nowadays there are several materials based on quantum dots, semiconductor quantum dots, and also the combination of that can be built to find the quantum confinement and the desirable material design. So you have a superconductor and then a quantum dot, and the superconductor quantum dot can generate the electronic state like this. This is a gap, and the Fermi level on both this side. This is superconducting gap. And the states close to the Fermi level are single particle state. They are due to the quantum dot, because quantum dot has discrete energy level. And you can generate various kind of junctions, pi and single normal junctions. So you have superconductor on the both side. The Cooper pair has to transmit through this state to the right side. So it can take several steps to go a bound electron from left side to right side. See this state. So here the upspin is intact, but the phase of this up-down is become down-up. So this is called pi junction. You can change the phase from here to here to the maximum pi. And this, if you change pi, the sign pi will give you a sizable phase to block the quantum states using quantum computing processing. Okay, so you can have a single pi normal junction also. That suppose this is the doubly occupied states. This is a Cooper pair. So first it will go single state here. This Cooper pair come here, and then the ground state of the you can say quantum dot now is intact, same, but this up down state is up down. So this junction does not change the phase. It keep the phase intact, just like the normal junction. But here the phase of the Cooper pair from up down is converting to down up. The total phase is opposing. So this is the beauty of the initial state, which is basically done by quantum dot. And it has very, you can say, high technological value to have hybrid material generated device which can form bits. So we have basically developed such kind of junctions. We have developed SQDS. My group has done a lot of many body calculations here. And this basic idea is that I equal to I sin delta can be changed, and the time derivative of this is 0. So it is not changing with time, only it is changing with the number of Cooper pair on left and right side. Those number of Cooper pair in a material are fixed. So this is the beauty. So you can have the Cooper pair, and its coherence length is very large, and you can generate the pi phase. So if you look at, if I have a quantum dot, you can see the quantum dot can generate the bound state on both this side. And these bound state are called Andrew bound state. You can see these bound state just like your P and N type of semiconducting states. Okay, and it is just like your semiconducting band, which you can dope by basically N type and P type donor and acceptor states. So these can be done by generating quantum dot and reflection of the Cooper pair at the John bound as the interface by generating pi junctions. So this is important. This can give you a Andrew bound state, which is the foundation of a qubit. Okay. So you can have a qubit realization, which I shown you in the last 4 to 5 slide, and the property of these qubit are realized by the Andrew bound state, and the qubit can generate Andrew bound state as the effect of asymmetry and the presence of the internal gap, and the asymmetry separates the upper and lower bound states, and it created a two-level system where you can block the occupancy only up to the first excited state. So you can engineer the order parameter by controlling the symmetry and allow to manipulate the energy level with the effective qubit, which is actually the idea a material scientist or a theoretician can give you some initial clues that which quantum material can be logically perfect to generate the stable quantum state and coherent stable states, which has less of, you can say, fidelity, may not leak information. So your information can be transmitted correctly from a point to the other point. Okay, so this is the basis of quantum computing. I hope you may be able to give you the flavor. Now, the main advantage of qubit are basically it is very easy, or its designability is quite fixed. You can have various kind of superconducting qubit now, flux qubit, phase qubit, and basically charge qubit. Its scalability is very high. It's so that it can be used for manufacturing the bulk system, and you can basically make entanglement. It is easy to couple to the other material, and it can be controllable also. But what is the disadvantage? That first is you need a room temperature superconductor, and somehow using AI or any computational technique, if somebody discover a room temperature superconductor, it will be the next year Nobel Prize. Okay, so this is the first advantage. Second disadvantage is the tunability. The size of the qubit is basically sometime give you the coherence time is not too large, because if you add another material, there will be some fiability or some errors. Okay, so superconducting qubit require some refrigerator, a dilution refrigerator, the cryo temperature, and also it's if we are able to justify with these, the superconducting qubit actually can be or is really a candidate where we can have a big processing of information, and it has all the qualifying criterion. So nowadays we are trying to follow the transpon qubit and JJ qubits. They are the multiplicity of the existing idea, superconducting qubit, because it is very simple and flexible to operate. And the XMON qubit is basically transpon qubit candidate. Okay, and using these qubits, you can generate corresponding logic gate. So idea is just like same. So what I'm saying is you can have a superconducting qubit on one side, you can have a bit based on semiconductor on the other side, and you can generate a system where a classical semiconducting system basically interface with a superconducting system. So these two things are still to be need to be understood by a you can say by metal scientist or by technologist, and there is a lot of opportunity for young faculties. Okay, so this is just capacitor and a gate is basically replaced by a Josephson junction. So instead of having ALC circuit, you have a Josephson. So you have a wire, an insulator, a wire. So you have this wire is superconducting wire actually. So you can generate gates, and instead of LC oscillator, you have the Josephson junctions. So you are building basically this kind of structure. This is a bit, you can say. So this is a sort of a standing wave. You might have seen just a particle in a box. So their phase are almost zero. So if the phase of a plane wave is zero, it means it is standstill march. Though still there is a transfer of information. Okay, so this is the hardcore beauty using superconducting qubit, and you can generate various combination of it by using circuit designing and basically using the optimization technique. Okay, you can use different geometry. You can take a circular ring also, Okay, this is a triangular ring, you can say terminal Josephson junctions, and so on. Okay, so the entanglement lifetime nowadays, if you look at the number of entanglement over the year from 2020 onward, अभी 2025 का मुझे डाटा इसमें नहीं डाला है मैंने, वो डालना पड़ेगा. We are going from say 4 qubit to around 2021, and nowadays we are going around 100 and that. But as a country, we are still looking to 3 to 4 bits. And though we have now various group for working in these directions and try to collaborate with the leading scientist or group in the world. Okay. So next is qubit control. So for qubit control, you generate a Hamiltonian with the total energy, and using this Hamiltonian, you can transform it by making certain transformations. You know, if cosine is transformed into cos and sine, so it means there is a plane wave, because only plane wave can have two components, x and y. So you can generate various kind of you can say tuning parameter by using the spin qubits, okay, mathematically also. And you can control it. You can have 2 qubit gate. You can calculate the total rotation. If you want to rotate a quantity, exponentiation, it is actually a short of the integral, which is called action. You might have done in the quantum mechanics. Okay. The rest is again gate formations, the swipe and C dot gate, and these gate can be generated. But still there is a lot of scope in this domain also, that which gate is more suitable and will be most stable in terms of the deviancy criterion. And there are also other material and other group in terms of the photon and nuclear spin, the semiconducting doped spin devices which are being claimed nowadays. Okay. So qubit control, you require the frequency tuning, you require the cross resonance to have hybrid material coupling, and then you need the parametric gates by using 2 qubits. And there should be a resonator which should be induced through a gate. And these are the steps further to have the qubit control, okay, using material, because everything is generated by material and fields. So you will try to keep the field aloof, only material and its combination. Okay. So you can have the qubit readout, and also the possibility of distribution is very less, because the coherence of the state is huge. And the system I am describing is superconducting system, where the superconducting quantum computing can be used to have a non-dispersive readout and highly coherent state. Okay. So there is a possibility to use filters also. Okay. The mechanism of this filter is beyond this talk, because that is itself is a big area. But that is a part of quantum computing. As a faculty, you must know that what are the possible qubit readout and filters which can be used, and the Josephson parameter to amplify, okay, are important. Okay, so now you have the possibility of readout in terms of the real time, and the candidate here I'm talking about the superconducting qubit. And next is the possibility of error correction. So during the transfer of data, there is the possibility of surface code, which can make you a system which is universal and scalable, basically generate you certain error at a threshold. And you can have a bosonic code also, because the bosons can interact with the source environment, because these bosons can also have a field and also have a electrostatic potential around. So you can have various kind of error, and one need to basically remove these error by using various kind of you can say scalability. You have to find various sample and try to understand which one is the best and have repeatability. So these are the basic design. There are then after that one should build a quantum computer based on this idea. There is a language also that is called quantum algorithm. So for every problem, every input, you have different kind of quantum algorithm. And these quantum algorithm can be optimized by using machine learning and quantum supremacy, which basically demonstrate that a programmable quantum device can solve a problem that a classical computer cannot solve. And a quantum machine learning actually parameterize a quantum circuit and provide a promising approach for exploiting potential of a nano device based on the quantum qubit. And you can use variational principle of the eigenstate. Variational principle means when the ground state and excited state are close together, and the eigenstate of the ground state and the excited state is orthogonal, then variational principle can be used. So the quantum algorithm implementation is much more promising in superconducting qubit-based system, and is also one of the central issue for quantum computing. Okay, so the last point, what is the conclusion and future outlook? There are in recent system days we have a lot of you can say increase in the interest of quantum computing based on superconducting qubit, and there is the advent of intermediate scale quantum device, and quantum computing will be used as a tool for computing tasks. It is gradually coming up with an increasingly important role in science, engineering, and also in the region which is not explored, just like space, just like you can say the ocean, and also deep earth crust. Okay, so those problems can be identified and solved and understand. So prediction can be made very quickly and very precise. So there is a great advantage of using a quantum computer in theoretical and experimental work, and can design more appealing approach for future. And there is a still need to develop and implement a very high quality quantum qubit based for quantum computer. And people are working hard. There is a lot of manpower need to be trained in these directions at intermediate and advanced level, and a lot of funds are being flowed by the DST on the name of the National Quantum Mission. And the quantum supremacy achieved by India is actually quite huge. And for quantum computers, it is actually next big milestone that will be basically faced by human or scientists in this world. And the near-term devices and develop a error-free, you can say, quantum computing, which is having no fidelity. There is no leakage of information, perfectly quantum system. And cyber security will be very, very strong using these devices. So a quantum leap is an advancement for a quantum mission, and for any country. I think if you look at India, we are quite ahead in this direction. Okay, so thank you. And these are some of the good references for graduate student and for faculty. There are some solicited book where this material is there, and there are Feynman lecture of physics, there volume 3, and then the final lecture on quantum computing. And also there are some paper of our group in European journal, where this work has been cited. And this super quantum computing is by Huang. This is one of the review, finest review. Okay, you can see. So thank you very much. So superconducting qubit-based quantum computing is technologically quite promising and prospective. And our country has already taken a quantum leap, and a huge advancement in terms of the mission has been implemented because of its lot of, you can say, significant practical importance. So I thank you for listening and for your attention. If there is any question, I'll... AD.
Yeah, thank you, sir. The floor is open for questions. So any
Yes.
participant who has any queries, any questions, they can go ahead, they can unmute themselves and ask the questions.
Oh, good evening, sir. Am I audible?
Yes. Yes.
Sir, my question is actually, I was wondering because since you are talking about the materials for quantum computers,
Hmm.
so there is a lot of research going on in the topological insulators and Rashba
Hmm. Hmm.
semiconductors and other novel materials.
Yes.
From what I understand, it is Rajba semiconductors are good for active error connection.
Hmm.
Topological insulators good for memory storage.
Hmm.
Sir, what are your thoughts that what kind of materials are better for quantum computers or
Okay. So
superconductors also can be made good candidates?
yeah, yeah. So what is a good name? Okay.
My name is Shardul Vadalkar and I
Yeah.
am
Yeah.
a lecturer of physics from
Okay.
Gujarat.
Okay. That's good. It's a very good question. Actually, if you look at the device through which I am making you presentation, is a semiconducting device. I'm making
Yes,
it
sir.
through laptop. You might all have. And this laptop has the basis of a semiconductor band gap. If band gap is not there, you could not transmit information in terms of a on and off device, which generate you 0 and 1 state only, not in between the two. Okay, you have 0 or 1.
Yes.
Okay, and it is because you have the Crony-Penny model had taught you by now that there can be possibility of reflection of electron from John boundary using Crony-Penny model, and there is a band gap. And this band gap in semiconductor, which is we are using, is a indirect band gap. I think you will agree. So the tip of you can say the valence band and the bottom of conduction band are not aligned. They are not at the same K vector. They are having some shift. So the total, you can say the energy which is being used as electrical energy and also the entropy of the system here
Yes.
is not, you can say, a good way to use computers and device because its efficiency, the device I'm using it, you are using, its efficiency is not more than 60%, 56% efficiency. And this efficiency is further being used to calculate data. You can see that in a final laptop, if you make it chargeable, it become heat up or not.
Yes,
So
sir.
why? It means that there is some loss of electrical energy and there is also some fidelity. If there is a system which is being used continuously, just like your bank computer or bank teller machine, so that machine will become more prone to fidelity. Because the data or the states which should be there in to transfer the data coolly will be destroyed and your information can be basically can be stilled up or maybe misinformed to somebody else which does not entitle. So these are the things which you everyone know. Now how to understand this as a quantum computing? This is also a quantum material. The semiconductor are also quantum material. The band gap is also formed by quantum mechanics to the solution of Schrodinger equation on the John boundary, and that is called the block wave function. So state
Yes, sir.
get localized. Here also I have shown you the block state. So there you have only translational symmetry. If you have rotational symmetry also, so it become a circle. Instead of having a two-dimensional lattice, you have a circular structure. So you are having localized block states in a quantum material where you can manipulate not the 0 and 1, but all states between 0 and 1. But how a material scientist will do it through material? We can do it or we can perform it using now many material. But one of the prone material I told you is superconducting devices based on Josephson junction. So a superconducting quantum dot junction make you possible help that, okay, your block states are now connected by various combination using junctions. Because the block state cannot be basically unpopulated or keep the localized to the ground state only if it is a harmonic potential. If you have to convert it to an harmonic, and if you convert to it an harmonic and still maintain the high efficiency, the coherence length or coherence time or fidelity time or direction of propagation should not change. It should be highly coherent. It should be robust in terms of the amplitude. Then what you will do? You will make a device that help you to have all combination, not at the cost of fidelity and errors, but a superconducting qubit. I think now you might have got some idea of your question. So what I'm saying, the good material still is superconducting material, but problem is we don't have room temperature superconductor. We are having liquid, basically helium or nitrogen, 77 degree Kelvin. And these are not very robust SVO system. So first thing, if somebody in some laboratory using AI or any model can predict that, okay, this kind of material combination in the predictable can give you 100% superconducting material at room temperature or close to room temperature. So I think it will become a very big scientific advancement.
Sir, actually, thank you, sir.
Hmm.
Sir, I had second question
Yeah.
because I read, I was
Mhm.
reading about the this year's Nobel Prize,
Mhm.
and my question was how it would affect the super, I mean the quantum computing and the
Okay.
spintronics
Yeah,
domain,
yeah.
and
Yeah, actually, yeah, this is again, I think if you have listened the Nobel lecture this year, so you are having as I told you, a Cooper pair which is coherent and we generate a gap at the around the Fermi level. And this gap is bound state, robust bound state, and it is a macroscopic gap. The superconducting phenomena is not microscopic, it is macroscopic, because instead of fermion, now you are having formation of Cooper pair, which are bosons. Okay, so the Cooper pair can follow the boson statics, and now this Cooper pair can be infinitely large in a quantum state. You got my point? So you can confine this Cooper pair close to the still ground state. Now question is how to connect this Cooper pair to the excited state. So you can connect these Cooper pair. I've shown you through quantum dot. You can basically sandwich a quantum dot between a superconducting wire. And this quantum dot basically allow still a Cooper pair to be bound at the macroscopic scale, because the coherence length of the Cooper pair is of the order of 10 raised to the power minus 4 centimeter. The quantum dot is of the order of, say, few angstrom or 100 and say 50 angstrom. So the coherence length give you the answer that the quantum state of a Cooper pair is macroscopically coherent, and it can tunnel from one superconductor to another superconductor even through a metal like of thing if the energy level of that metal are of the order of the superconducting gap or milli-electron volt. So the energy level of a quantum dot are of the order of milli-electron volt. You know, for hydrogen atom, the energy gap are of the order of 13.6 upon n square, are of the order of 2 to 3 electron volt, which is huge. So by making a few atoms together, you can reduce that size. Okay, so you can make the quantum tunneling at a macroscopic scale through a normal material. The question is that normal material has the temperature basically close to the transition temperature of the material or superconducting material. Then this state will be visible. Otherwise, its coherence may be lost because Cooper pair will not survive above the transition temperature. So this Nobel Prize said, okay, the Cooper pair can be connected through a metal at a macroscopic scale, and there can be tunneling. You can see not in the atomic regime, but in a mesoscopic regime. So you have between nano and bulk material, that is another regime where it's called mesoscopic or macroscopic now, which can be seen by some atomic devices also. Because we can see atom by some atom also. You see atom on the surface by scanning tunneling, isn't it? How you see atom and their arrangement? Through tunneling or through scanning. Surface atom can be seen by through scanning, tunneling, and by deep states close to the Fermi level can be seen by tunneling. So you have basically quantum tunneling, which give you how the states are spread around the Fermi level. And this feature are, you can say experimentally, every material laboratory has these four fundamental experiment: a synthesis, a vacuum chamber, XRD, FASM, scanning tunneling, and then surface states, which you say topological. So surface states are disconnected from bad states, which I am telling you. Right now, I am telling you that you have bad states. Bad state are the deeper atoms, which have certain arrangement. Surface state are not connected to the band state, and these surface states are called topological states. So you can spread the surface states by using some scanning devices on the surface and understand them, how they are spread. But sometimes the deep band state electron can come to these surface states by making certain energy jump or finite probability, because you cannot stop electron going to the quantum states. The probability of electron to exist in all the state is finite. Of course, in certain state, where boundary conditions satisfy, the probability of finding the electron can be maximum. So that the sum of all probabilities is 1. So this is how quantum mechanics and its measurement goes.
Okay,
Any other question?
So it was a very enlightening and
Yeah. Okay, I think this is a magic actually. If you understand quantum mechanics, I think it is easy to understand. But if you understand classical mechanics, you are really a sophisticated person. So what I'm saying is, I just give you a clue. Please understand the classical mechanics from Hamiltonian to Lagrangian formula and action, and its crossover from Poisson bracket to computation relation. Then your insight will be very strong. Because from classical to quantum, the transition is not smooth. The transition is adiabatic. It is discontinuous. So that feeling can only be done by some deep understanding. So go to the Goldstein again, and some of the Russian, classical mechanics. So you will understand that, okay, we don't understand the quantum mechanics very well, because Schrodinger equation fails. It was predicted by Einstein and also Feynman. It is a partial wave equation. You require four boundary condition into to a partial equation. तो आपके पास एक solution होना चाहिए. You must have a solution, non-solutions. So for one-dimensional solution, Schrodinger equation, you require 2 points where solution is known. For 2 dimension, you have a 2-dimensional spaces 4 boundary. So you require 4 boundary condition where solution is known. But for a scientist in laboratory, how he will be able to establish a material where the solution exists at 4 point, and you know the solution. At least you can know the solution at some initial magic state, or by making certain permutations. And mathematics cannot give you exact solution, because the things I'm telling you all, because of my experience in this theoretical area, we are not able to solve things exactly most of the time. But we accept nature. If things are not solved exactly, let us accept approximate solution, which give you some understandable or some computational data which can be used for further action. Because the very core fundamentals we have does not allow us to have exact solution. Only few non-problem solve exactly. But these problems or these type of solution cannot provide you practical applications, but give you a basis to understand more extended view. This is how things go.
यस सर। सर एक्चुअली वही प्रॉब्लम, मतलब वही प्रॉब्लम है ना सर, कि जब हम लोग क्लासिकल से स्टार्ट करते हैं तब हमारा जो अप्रोच रहता है वो डिटर्मिनिस्टिक रहता है, लेकिन जब क्वांटम पे आते
Yeah.
हैं तो और वो प्रोबेबिलिस्टिक हो
But
जाता है।
yeah, but quantum actually has only few problems which are exactly solvable. You have only harmonic oscillator and also the hydrogen, even hydrogen atom, single atom. But if it is a relativistic hydrogen atom, it is Sommerfeld.
यस
So hydrogen atom is also a approximation because you say only spherical orbit. But if you use relativity, no. Most probable of orbital is elliptical. If you see that electron are relativistic in character, you have Sommerfeld correction, na? And then spin orbit
sir.
coupling. Then angular momentum come into picture for elliptical orbit. For circular orbit, it becomes silent. So that's why the hydrogen atom, due to Bohr, is a pedagogy. But real physics is it is elliptical. The nature has elliptical orbit. Even our galaxy, if you say अंडे ब्रह्मांड जैसा एटम है वैसा ही हमारा गैल है, हमारा ब्रह्मांड है. So we still at the approximation, in the very core of our understanding. But classical mechanics, I am telling you, if you understand and make yourself devoted to that, it is really sophisticated subject, and it can give you a lot of understanding of which pure quantum mechanics cannot give you.
Okay,
So
sir. Thank you,
mathematically,
sir.
it
Thank you
sounds
very
simple.
much.
Okay. Yeah.
Yes, sir.
Yeah, any other queries from the participants? Okay, if there are no further queries, let's conclude this session with a vote of thanks. So I'm Dr. Ashish Vanmai from Vidyavadini College of Engineering and Technology. And I take this opportunity to thank Dr. Ajay for giving deep insights of superconducting qubits and how we can use it to process information and implementation of quantum algorithms. Also, sir has given us direction for future work. So some of our participants can pursue their career and contribute to quantum mission of India. So from the entire team of VCET and from all the participants, I thank Dr. Ajay for conducting this session despite his busy schedule and sharing his knowledge in this domain. So thank you, sir, very much for this session, and we can conclude the session now.
So thank you very much to the organizing and for a nice introduction. And also there was very good questions. I think I hope that I may be able to come through. And still there are real-time problems. There is a lot of opportunity. And now even if you are at a engineering college, you still have a lot of, you can say, way to contribute and to improve yourself. So thank you
Surely, sir.
for giving me this this opportunity. And my location is here at this time. I am at Gurgaon, so I was here. Tomorrow I am having some interaction with the IT Delhi, so I am speaking from here. So thank you. Okay.
Yeah, thank you, sir, once again.
Okay.
Thank you, sir.
Okay. Thank you, Dr. Neha,
Thank you, sir.
and everyone in the team and all the participants.